All right. Yeah, so today I wanted to talk about uh, a very brief crash course in models for Infinity One categories and how do model categories specifically fit into the picture. Um, and without further ado, let me list perhaps four most important models which you can see in this list. These will be relative categories, quasi-categories, complete single spaces, and simplicial categories. And I wrote some possible uses for these definitions. But let me maybe offer some comments first. So model categories are closely tied to relative categories. So we'll discuss them in a few, maybe in the second part of today's lecture. But perhaps it makes sense to point out that relative categories were the original example of Infinity One category, and that was even before all the other models showed up. A relative category is simply, I think we already gave a definition before, just to remind you, a relative category is simply a category C together with a with a specified subclass W of morphisms. Uh, Elements of W are called weak equivalences. And the only requirement we impose on W is that W is closed under composition and contains all identity morphisms. In particular, as a subcategory, W is going to have the same objects as C, but of course, it's not going to be a full subcategory. And moreover, you think of the elements of W as morphisms, you will eventually like to invert, um, not in the strict sense of this word, but in some homotopy coherent sense. And for now, let me also mention one more model, which is a simplicial category. This is just a category enriched in simplicial sets, meaning you have a set or a class of objects, and between any pair of objects, you have a simplicial set of morphisms. So if C is such a simplicial category, then for any pair of objects, you have an enriched object of morphisms from X to Y. And these enriched objects compose, they have an operation of composition that works in the obvious way and satisfies the obvious axioms. The other two models, like I mentioned, which is quasi-categories and complete Siegel spaces, and the closely related Siegel categories, which I didn't even bother to mention here, all of these will be explained when we need them. So for now, let me just mention that relative categories, basically that's the original example of Infinity One categories. It is particularly easy to give examples of relative categories. But also concrete complications are very easy to do, especially in the presence of a model structure. And that's why I also mentioned model categories in the same line. Quasi-categories are very useful for theoretical constructions. The uh, uh, in fact, quasi-categories can be organized into a model category, and fibrant objects in this model category will be precisely quasi-categories. And this model categories has a bunch of very nice properties. It is a Cartesian model structure, and all objects are co-fibrant in this model structure. And this allows you to sort of do tricks that you wouldn't be able to do in the other model, the model of relative categories. Relative categories, in fact, also have a model structure, but its theoretical properties are terrible. Cofibrancy is very difficult. Fibrancy is also quite non-trivial, and for that reason, we'll see later that you have a whole bunch of additional difficulties you wouldn't have with quasi-categories. Complete single spaces and similar models are very useful for writing down examples, I would say, of geometric nature, like Bordism categories. And the reason this happens is that in geometric situations, the operation of composition is typically going to be defined using some kind of geometric operations which tend to be not strict. They tend to be not strictly associative, but maybe coherently associative. And single spaces and similar formalisms are ideally suited for encoding coherently associative structures. And finally, let me also mention simplicial categories. This is really an auxiliary model, I would say, but it's quite useful in several theoretical constructions. And also it sort of quickly conveys the main idea of an infinity one category, that you should think of an infinity one category as a category enriched in the appropriate model for spaces. And what better conveys this idea than category enriched in simplicial sets? We have seen that simplicial sets are one of the many equivalent models for categories. And there are many comparison functors between these models. So as I mentioned, or maybe I should mention explicitly, that all these models are equivalent models, where equivalent will actually be explained a bit later. Well, with the exception of model categories, all the other ones can be organized into a model category, which is kind of ironic. But and these model categories will turn out to be equivalent. Um, all right, so I mentioned relative categories, and we'll see many examples. For example, simplicial sets and weak equivalences, or the category of all small categories and equivalences of categories, or the category of groupoids and equivalences of groupoids, um, or the category of topological spaces and weak homotopy equivalences, or the category of smooth sets, which we studied closely previously, and weak equivalences that are transferred from simplicial sets using a smooth singular complex functor. or the categories of simplicial abelian groups and chain complexes with quasi-isomorphisms, differential Gregor algebras and their quasi-isomorphisms, commutative differential Gregor algebras. So as you can see, there are plenty of practical examples. And perhaps one thing that may not be obvious in those practical examples is how, for example, I mentioned that simplicial categories and relative categories are equivalent models, and we may be wondering how exactly does such a simple structure, such as a relative category, give rise to a simplicial category. And this is a hardly an obvious question. In fact, the theory of such so there are several functors going from relative categories to simplicial categories, and they were all constructed in, I guess, 1980s in a series of papers by Dwyer and Kahn. And it's hardly obvious how to do this correctly. So let me at least demystify relative categories for you by presenting at least one such construction. And the reason I want to do this is, at least in my experience, for example, when I studied model categories for the first time a long time ago, I wasn't aware of this construction, and perhaps for that reason, the notion of a model category appeared at least a bit mysterious. It wasn't always clear why some constructions we do with model categories are correct. And maybe question?
Sorry, yeah, maybe a quick question. So it seems that whenever we have some kind of model for infinity categories, this kind of model, so the collection of the inhabitants of this model always form some kind of model category. So and the model category itself is an infinity category, but a very specific kind because it has this extra model structure, as you mentioned. So why is it that model structures, like, is it from experience that we know that such a model always forms a model category? Or is it rather that there is an intrinsic meaning to why it has to be a model category? Is there something that makes them special aside from being computationally very efficient?
Yeah, I mean, I would say it's a good point. I mean, model categories originated in late 1960s in the work of Quillen, where basically Quillen observed that in various settings in homotopical algebra, you tend to do the same arguments over and over again. And basically what Quillen said is, let's do it once and for all and get rid of this endless repetition. And one of those, a lot of those properties have to do with lifting properties. Like, for example, cofibrations have a lifting property along acyclic fibrations and similar ideas. And I would say it's actually not entirely true, perhaps, that we do know model categories for all possible models of infinity one categories, but the exceptions are maybe they have fallen out of use in part for that reason. I think I mentioned maybe last year that in the 1990s, there were a whole bunch of models, well, they still exist, but hardly used anymore, the so-called algebraic models for higher categories. And there was a whole bunch of those definitions by, well, there are far too many people to enumerate, but you can always open the NLab article on higher categories and you will see a list a very long list of models that were presented or constructed in 1990s. And as far as I'm aware, quite a few of those models have not been organized in a model category. And which does make it more difficult to study such models for higher categories. In fact, I would say one of the main insights of the 21st century is that you really do need a lot of homotopy theory to study higher categories. And a lot of homotopy theory, I mean stuff like very hardcore stuff like model categories and maybe quasi-categories and similar formalisms. And what was done in the 1990s, a lot of these attempts were basically trying to define infinity n categories without really using much homotopy theory. And perhaps for that reason, well, the other reason, of course, was that these definitions were fairly difficult to manipulate. They typically required a lot of coherence expressed algebraically, and that required a lot of effort to do. And perhaps these days, when homotopy theory developed so much, we could revisit those older models and perhaps bring them in the model categorical setting, but I'm pretty sure nobody is seriously trying to do that right now, with a possible exception of some French people who are working on some algebraic strict algebraic models for infinity n categories. So it's I would say it's at least partly a selection effect that only those models that were easy to manipulate, that were easy to prove theorems about, only those models survived in our mind, so to say. And of course, only those models for which it was easy to construct examples. And the main problem with constructing examples for those other models from the 1990s was that you had so much algebraically expressed coherence that it was simply difficult to construct any practical examples. Yeah, so it's basically a combination of factors that we ended up selecting those models that were easy to manipulate theoretically and were easy to construct examples for. So somehow this magically selected examples that organize themselves in model categories. Yeah.
Thank you.
You're welcome. All right. Now, let me very briefly explain this construction that takes a relative category and constructs a simplicial category. And one of those constructions is called the hammock localization. And you will see why hammock in a second. Well, you can see this picture here, which does look like a hammock. So it's obviously descriptive. Okay, so let's suppose somebody gives you a relative category C with weak equivalences W. And you want to construct a simplicial category D, so traditionally denoted by L with a superscript capital H of CW. So this is what is called hammock localization, H and L for hammock localization. And this category, this simplicial category, is going to have the same objects as C, whereas morphisms are now going to be a bit complicated. if you have two objects, x and y, you want to construct a simplicial set of morphisms from x to y. So dxy will be a simplicial set. And the n simplices, so let's pick some n simplex, and the n simplices in the simplicial set of morphisms will be equivalence classes of such pictures as depicted here, where you have, in this picture, you would have n plus 1 rows. So here you see you have 3 rows. So this example corresponds to n equals 2. This is a picture of a true simplex. And perhaps I should mention right away that the construction will end up looking very similar to the construction of a nerve, except that it won't quite be a nerve. But we'll see in a second that it does look very similar. So let me say a few more words. So you have x on the left, you have y on the right, and you have these commutative diagrams in the middle. So each square is commutative, and all the triangles are commutative. All vertical arrows are weak equivalences, so each vertical arrow is a weak equivalence. And the left pointing arrows are also weak equivalences. So this arrow, for example, is a weak equivalence. This one is a weak equivalence. And the only arrows that will allow not to be weak equivalences will be the ones that point to the right. So for example, this arrow from x11 to x12 will not be a weak equivalence. And now you're also introducing equivalence relation, which says that if you have two columns pointing in the same direction, so that's what I mean by composable. So if two columns, so imagine in this column arrows were pointing to the left, then we would allow composing such two columns in a single column. And likewise, we can also insert an identity column for free. So that's an equivalence relation. And now we get equivalence classes with respect to this equivalence relation. And that's what an n simplex is. And in particular, maybe we should mention that zero simplices in the simplicial set will be chains of morphisms from x to y, like depicted on the left. And the left pointing arrows will be weak equivalences. And basically, this is how also you construct. Remember, last year we talked about the ordinary, so this is called the category of fractions. AKA homotopy category. And you think of it as inverting elements of W formally. And this is exactly what is happening here, where you see you have a formal chain of morphisms connecting x and y, and the weak equivalences are allowed to go in the wrong direction. So we want to interpret this chain as a morphism from x to y, which is a composition of individual elements in the sequence, and weak equivalences pointing to the left these guys you can think of as being formal inverses of the same weak equivalence pointing to the right. So the zero simplices in a hammock localization are precisely the same as you would take in the usual construction of the category of fractions. So in particular, as it turns out, if you take homotopy, if you take connected components, so pi zero of the simplicial set, you will see precisely morphisms in the usual homotopy category. So the new ingredient now is that you have higher simplices, and these higher simplices can encode non-trivial homotopical information about the space of morphisms. And as I said, if you look at this picture, you will see that each row looks like an object in some category, and each row of morphisms looks like a morphism, right? So these vertical arrows, you can think of them as morphisms between two such chains. And that's why I said this construction looks almost like the nerve of a category, because a hammock of height n with n plus 1 rows, it does look like a chain of n composable morphisms expressed by these vertical pointing arrows. So this looks like a chain of n morphisms from the row on the top to the row on the bottom. But ultimately, this turns out to be not quite true because of the equivalence relation. So the equivalence relation. So if you fix the number of columns and their types, whether they point left or right, then for a fixed geometric shape of such picture, you do see the nerve of a category. But the moment you introduce the equivalence relation, it ceases to be a nerve. Okay, so, and as you can obviously imagine, such pictures can be composed. Let me maybe draw at least one composition here. Imagine I have, say, two different true simplices. Let me point in the opposite direction just for fun. And here is one more. Let me make this one short because why not? This will be a hammock of with only two columns. And in the middle, you have some vertical maps, which are weak equivalences. And two such pictures can be composed in a very obvious way. You simply imagine joining two pictures together, and this vertex, you would sort of stretch it out and insert identity maps as vertical maps here. I'm not even sure if I should draw it, but let me just very quickly draw a picture. And so the, let's see, The green arrows are identities. And that's how you compose hammocks. You can easily verify that the equivalence relation is respected by the composition. And this gives you a well-defined simplicial category. And I hope this demystifies somehow, at least a little bit, the notion of a relative category to you. Of all the existing models for infinity one categories, it is perhaps by far the most mysterious and potentially confusing. And now that you know how to produce a simplicial category out of a relative category, I hope it seems at least a little bit less mysterious. All right. Any questions so far?
Does this localization functor fit into an adjunction?
No. In fact, it is possible to write down a weakly equivalent functor called the standard simplicial localization, and this one will fit into an adjunction. But you can see that this functor, the hammock localization, it doesn't respect limits or co-limits because, well, typically the nerve construction will at least respect limits, and this hammock localization almost respects limits. In fact, if you fix the type of a hammock, then it does respect limits, arbitrary small limits. But because of these equivalence classes that we have to take, limits will not be respected anymore. So the hammock localization functor is not really a left or right adjoint in the traditional sense. Of course, I mean, we do know that ultimately it will turn out to be an equivalence of infinity one categories. So in that sense, it is an adjoint functor, but if, in fact, even an equivalence. But this is only an equivalence in the appropriate homotopy coherent sense. But yes, so the hammock localization, I guess you could say it's a construction. In fact, it defines a relative functor from the relative category of all relative categories to the relative category of simplicial categories, where a weak equivalence of simplicial categories is defined as what is called a Dwyer-Kahn equivalence of simplicial categories, which is a homotopically essential surjective functor that induces weak equivalences on objects of morphisms. And Dwyer-Kahn equivalence of relative categories, well, the easiest way to define it is to transfer weak equivalences from simplicial categories using the hammock localization. So that is one possible definition. Yeah, so the answer is no in the most traditional interpretation, but yes, once you go homotopy coherent, and so the hammock localization functor does define the appropriately homotopy coherent notion of adjunction and even an equivalence of relative categories. Yeah. But as I mentioned, there are other models that are weakly equivalent to the hammock localization, like the standard localization, which do form also a strict adjunction.
Thanks.
All right. Yeah, well, you're welcome. Let's move on to model categories. And let me also demystify model categories. At least clarify one point immediately, which was not obvious to me until at least when I first started to study model categories a long time ago. So, and the thing to emphasize is maybe the most natural way to think about model categories is that a model structure is first of all defined on a relative category. And on a relative category, you have to specify some auxiliary data, which is auxiliary in a very precise sense that it's just changes the way you do your computations, but the final answer to those computations will always be weakly equivalent to any other answer you can get. So a model structure never affects anything about the final answer to your problem, but it does affect the specific presentations you choose for your intermediate computations. And just to give you maybe a familiar example from homological algebra, in homological algebra, you have projective resolutions and injective resolutions, and maybe some other types of resolutions like flat. And all of these guys are, their choice is ultimately irrelevant for what you want to compute, but they do affect the specific presentation of intermediate steps in your computation in homological algebra. So a good way to think about a model structure is that it basically is a choice of resolutions for your relative category. So it doesn't affect anything on a fundamental way, but it does affect your computations quite a bit. And depending on the chosen model structure, your computations may simplify quite a bit. But nevertheless, perhaps a good thing to point out that model categories with the same underlying relative category are all equivalent to each other. So let me define model structures. Here is maybe a modern definition of a model structure. So as I said, we are going to be defining model structures on a relative category. And such a model structure consists of two classes of maps called cofibrations and fibrations. These classes of maps are classes of maps in the underlying category C, and two conditions must be satisfied. And the first condition is a condition on the underlying relative category, so we always impose this true out of 3 property on the relative category. And the true out of 3 property says if you have two composable morphisms, F, G, and here is a picture of their composition, F composed with G, and 2 out of 3 of those morphisms are weak equivalences, then so is the third one. So if F and G are weak equivalences, and so is F composed with G, which means that weak equivalences are closed under composition. But also if the composition is a weak equivalence, and one of F or G is a weak equivalence, and so is the other. And the other property is that if you check the class of cofibrations, and the class of fibrations intersected with the weak equivalences, or the class of cofibrations intersected with weak equivalences, and the class of vibrations, you get what is called a weak factorization system. What is a weak factorization system? Well, more generally, if you have a category C and two classes of maps, L and R, which obviously stands for left and right, then you say this pair of classes is a weak factorization system on C if any morphism in C can be factored as a composition of a morphism in the left class followed by a morphism in the right class. So L and R are elements of capital L and capital R respectively. That's what the factorization part stands for. Any morphism can be factored as a composition of a morphism in the left class and a morphism in the right class. And the other property is the familiar, I hope, lifting property from algebraic topology. It says, well, in its original form, it says if you have a commutative square, here's a commutative square, and the left morphism belongs to the left class, so L is an element of capital L, and the right morphism belongs to the right class, so R belongs to capital R. Then it is possible to find a non-unique diagonal arrow, D, that makes both triangles commute. And the fact that this arrow, so D is non-unique, is what the weak adjective is for. So weak scans precisely for the fact that the diagonal arrow here need not be unique. If it is unique, then it's called just a factorization system or orthogonal factorization system, and it's a much stronger notion. But in our case, we demand even a bit more. Not only we demand that every pair of morphisms from L and R has this property, but we also demand that L and R are determined by the lifting property. And what I mean by this, for example, is that a morphism belongs to R if and only if it has a lifting property with respect to all elements of capital L. So you can see this expressed formally here for any element of capital L and for any A and B horizontal morphisms that make the square commute. It is possible to find a diagonal arrow D that makes both triangles commute. So this property characterizes being an element of capital R, which is what I mean by this formula here. And there's a perfectly symmetric property for capital L. And this last property is sometimes, so the second bullet point, if you is sometimes called the closure property. And this property was not imposed in the original book by Quillen from 1967. It was, however, added just 2 years later, in 1969, in Quillen's paper Rational Homotopy Theory. But because of that, up to even today, sometimes you would see in the literature people talking about a closed model category where they mean that this closure property is included. But I think it's safe to say now that all model structures are now considered to be automatically closed. But yeah, the original definition only had this lifting property. So for any L and R, you have a diagonal arrow D, but it concluded the closure as a separate property, not in the main definition. All right, so let's give some examples. Any question about the definition maybe first? Let's do maybe since spaces are the most typical possible example of an infinity one category, and I mentioned that that model categories are supposed to be models for infinity one categories, and that's where the word model comes from. So a model category is a model for an infinity one category. Therefore, it would make sense to start with simplicial sets as an example of a model category. And some classes maybe most classes are actually fairly easy to define. So cofibrations will be monomorphisms, meaning so a monomorphism of simplicial sets is just a degree-wise injection. So maps on n simplices are injective maps. Fibrations are what is called a confibration. So we say F is a confibration if it has a right lifting property with respect to the so-called Horn inclusions. So what is lambda and delta n? Well, first let's recall that delta n is a representable simplicial set. Let me draw a picture for n equals 2. For delta 2 is going to look like a true simplex. And what we can do for such a simplex, we can first remove the top-dimensional face, the two-dimensional face in this example. So here is the boundary of delta 2. It's just 3 one simplices glued together without the top-dimensional face. And if you remove one more of these, one of these 3 faces of codimension 1, you get what is called a horn. So for example, here is lambda 2, 1. And here is lambda 2, 0. And here is lambda 2, 2. So the number k tells you the index of a vertex, and you remove the face opposite this vertex. So here is vertex 0, 1, and 2. If you take this triangle and remove the face opposite 0, this will be this line segment. So that's why lambda 2, 0 is these two guys. You removed the face opposite 0. And the same is true for the other two horns. Yeah, so that's what a confibration is. So a map from X to Y is a confibration if for any horn mapping into X, if once you map this horn from X to Y, you can fill it with a simplex, then this filling can be lifted to X. That's what the confibration condition means. Let me also mention the other two classes of maps. In principle, also admit explicit descriptions, the intersection of fibrations and weak equivalences. So that sometimes in the literature model categories is known as acyclic fibrations. And sometimes also as trivial fibrations. And these maps can be characterized using a lifting property with respect to inclusion of a boundary of a simplex into a simplex. So that's a much stronger property than before. So before we could extend a map from a horn to a simplex, and now we can extend a map from any boundary of a simplex, which is a much more difficult thing to do. And intersection of W in weak equivalences and co-fibrations will be the so-called anodyne maps, which is a notion studied in simplicial homotopy theory. Let me not try to explain much of it here right now, but in case you're interested, these will be codomain retracts of transfinite compositions of co-base changes of horn inclusions. And this description is a highly typical description of acyclic cofibrations in a model category. The only thing that will change is that for other model structures, horn inclusions will be replaced by a different set of maps. And finally, let me mention a few ways to define weak equivalences in this model structure. So weak equivalences of simplicial sets, they can be defined in many ways. I just listed 3 constructions here. And perhaps given what we just did already, we can, since we already defined acyclic, so these are called acyclic cofibrations. Since we already explicitly defined acyclic cofibrations and acyclic fibrations, as it turns out, the axioms of a model category guarantee that any weak equivalence can be presented as a composition of an acyclic cofibration and an acyclic fibration. So that's one possible definition of weak equivalences. Another definition is that a map F from X to Y is a weak equivalence if for any Kahn complex K, so a Kahn complex is just a simplicial set such that the map to the terminal simplicial set is a fibration. And this notation here, double arrow, is sometimes what you denote fibrations by. Let me actually give you standard notations for all 5 classes of maps. So cofibrations will typically be denoted as an arrow with a little sort of feathers at the other end. Acyclic, so fibrations would be denoted using a double arrow. if you have a weak equivalence, you would put a tilde on top. Of course, just weak equivalences would be denoted using a single tilde.
Please may you reveal a bit intuition about configurations? Some intuition behind of this term.
Yeah, in fact, we will see an example with conf vibrations maybe in a simpler setting. For now, let me just say that there are many reasons why you want to have conf vibrations. Perhaps one thing to mention maybe is that fibers of conf vibrations are well behaved, in a sense that if you pick an arbitrary point in Y, an arbitrary zero simplex, and extract the fiber of this map, so basically all the stuff that maps to this vertex, this fiber will be well behaved. And one way to express it is to say that the map from this fiber to the homotopy fiber will be a weak equivalence. So fibers of conf vibrations are well behaved. That's one nice property. And the other nice property is that maps to a concomplex are well behaved. And you can, in fact, see this property being used in this description, where I describe weak equivalences as maps from X to Y, so that for any concomplex, the map from the induced map on simplicial mapping spaces will be a simplicial homotopy equivalence, meaning there is a map in the opposite direction, and the two compositions are homotopic to the identity map.
Am I right that this is maybe considered as a tool for obtaining weak equivalence, yeah, configuration? It is some kind of tool, if we roughly speaking.
This description can be used as a definition of a simplicial weak equivalence, yes. So you can, in fact, take the second formula as a definition. In fact, a similar description exists in arbitrary model category. You would say in an arbitrary model category, you would say a map between, say, cofibrant objects is a weak equivalence if this map here on simplicial mapping spaces is a simplicial homotopy equivalence. Yeah. These two definitions may not be the most easiest, perhaps, to manipulate in practice. Here is one more. There is a functor x infinity, which you can construct completely explicitly. It's what is called a con-fibrant replacement functor. And it replaces any simplicial set by a weakly equivalent concomplex. And then you can say a map F is a weak equivalence if, after applying x infinity to F, we get a simplicial homotopy equivalence. And this definition may be a bit easier to comprehend. Let me perhaps draw some more pictures, since the question of intuition for conf vibrations and complexes was raised. Let me maybe offer a geometric application. for Kohn complexes. And the slogan here is like a Kohn complex, which is defined as a simplicial set K, for which the canonical map to the terminal simplicial set is a fibration. A Kohn complex is the same thing as an infinity groupoid, meaning a type or a notion of a higher category where you have morphisms, K morphisms for all K. And these K morphisms are invertible. Let me now explain how to interpret a Kohn complex as an infinity groupoid. So let's say K is a Kohn complex, and elements, so vertices of K, we interpret as objects. One simplices so here is a one simplex. Well, let's say the true vertices will be x and y. And the one simplex itself is sigma. We interpret such a one simplex as a one morphism. It will be one morphism from x to y. What about true simplices? Here is a true simplex. X, Y, Z. As we just discovered, morphisms, one simplices should be interpreted as morphisms, F, G, H. So F will be a morphism from X to Y. G will be a morphism from Y to Z. H will be a morphism from X to Z. And you have the gate of a simplex that fills it in. Let's call it tau. Yes, tau is fine. And you think of tau as a morphism or a homotopy from the composition of F followed by G to H. Recall that or if you prefer, another name for homotopy is a true morphism. Right, so I promised you K morphisms for all K. And here is an example of a true morphism. And here it's important to point out that this composition that I wrote here, this is just a formal notation. There is no actual strictly defined composition in a Kohn complex. Rather, the only thing you have is this interpretation which basically allows for composition to be defined formally. But notice that any true morphism is invertible, so the existence of such a true morphism postulates that H is isomorphic to G composed with F. So tau, by virtue of being interpreted as a true morphism in an infinity groupoid, you should think of tau as an isomorphism. Which sort of tells you that if you want to compose F and G, well, you should just find H isomorphic to the composition. And how can you find H if you know F and G? So let's insert another page to compose F and G, find some H isomorphic to G composed with F. And of course, this phrase should be interpreted formally. In other words, to compose F and G, let me draw a picture. Here is the gauge of F and G. So to compose F and G, the procedure tells us find a true simplex tau that has F and G as true of its sides and has some other third side, which we are going to call H. Okay, so the procedure for composing morphisms tells us to compose true morphisms, you would organize them into this geometric picture, and then you would find a true simplex that fills out this picture. And of course, this picture is nothing else than a map from a true form, specifically lambda true 1 true k. Because lambda true 1, let's recall, on maybe the left side, yes, here is a picture of lambda true 1. You take a true simplex, you remove the top-dimensional face, and then you remove the face opposite to 1, so this bottom face, and you get lambda true 1, the two-dimensional horn. Whereas the gauge of tau on the right is a map from delta 2 to k. So we see what happened here is that we were given the gauge of F and G, which organized itself into this horn because the codomain of F was the same as the domain of G, this point Y, where they join together. So the input gauge was this map. And then somehow we managed to say, okay, we really should be able to extend it to compose F and G, we should be able to extend it to a map from delta 2. And if you look closely, you will see that, of course, this is just our favorite and familiar lifting property, because if you imagine extending this diagram by the terminal object, any true maps to the terminal object must coincide. So this bottom triangle is going to commute automatically. And this lifting exists because this map is a fibration. By definition, K was a Kahn complex. So this map is a fibration. Yeah, so that's how you interpret a Kahn complex as an infinity groupoid. And perhaps, I mean, there are, of course, many others to explain. For example, why are all morphisms invertible? Let me very briefly mention this. How to construct inverses of morphisms. Well, imagine you have a morphism F from X to Y. What I'm going to do now, I'm also going to consider the identity morphism from X to X. So this is identity. What's called the identities are just degenerate one simplices. So identity on X is simply the degeneration of the vertex X. Any vertex can be degenerated to a one simplex, and this gives you the identity morphism on this vertex. But now you see that the gauge I drew here is also a horn. It's lambda true 0. And since K is a Kahn complex, I can fill it out to a true simplex. So I'm going to see a true simplex X, Y, X, F, identity, and here is some G. And according to the interpretation of true simplices, the composition of G and F will be homotropic to identity, which means we just constructed the left inverse of F. And of course, the right inverse is constructed using the other form. So any morphism F has a left inverse and a right inverse, and you can easily prove that these two inverses are homotropic to each other. So the intuitive meaning of Kahn conditions is that the Horn lifting conditions are that the conditions that guarantee existence of compositions and inverses. And of course, the story doesn't stop here. You can also ask, for example, I mentioned that to construct composition, you would fill out this horn by a triangle. But of course, you can immediately ask a question: what happens if since the lifting is highly non-unique, I can always choose a different triangle that fills out the same horn. And the answer here, of course, is that yes, compositions will not be unique, but any true candidates for a composition will be homotropic. And the homotropy will be constructed itself using a horn filling property for a dimension 3. When n equals 3, you will see a tetrahedron. Its three faces will be filled out by a tetrahedron And such a property can construct a homotopy between any two potential candidates for composition. So even though composition is not unique, it will be unique up to homotopy. Okay, any questions about the model structure on simplicial sets? And since we always also mentioned quasi-categories in about half an hour ago, maybe I can mention that quasi-categories are defined exactly like a concomplex, with the only difference being that you exclude the so-called outer horns, which correspond to horns where the vertex k is the initial or terminal vertex in a simplex, which in dimension 2 would correspond to these two guys here. And the effect of this is that you are no longer able to construct inverses in this manner. So inverses are no longer guaranteed to exist. But you do have compositions as before, and compositions are defined in a homotopy coherent fashion. All right, let's move on. Maybe I want to mention maybe a few more elementary examples that can also be helpful to understand various aspects of the model structure and simplicial sets, which, by the way, is sometimes called these days the conquivalent model structure. But this is a fairly recent term, structure, which apparently was introduced on the NLab at some point in the past. All right, so here's a model structure on the category of small categories. So cat has as objects small categories, meaning objects form a set and morphisms form a set, and morphisms are functors. And groupoid is another such construction where objects are groupoids and morphisms again are functors. Then there is a model structure on such a category, sometimes called natural model structure or canonical model structure, or sometimes also the categorical model structure. And a term that is increasingly falling out of use is the folk model structure. Maybe I should still mention it. And let me put it in quotes because it's not really a folk. The first exposition is due to Joyal and Tierney. From 1992. Yeah, in this model structure, all three classes are very easy to describe. Weak equivalences will be just equivalences of categories. Cofibrations will be functors that are injective on objects. And fibrations will be functors, certain functors known as isofibrations. Iso refers to isomorphisms. So the definition here is really simple. Functor P is called an isofibration if for any object in its domain and for any morphism phi from its image to some other object B, if this morphism is an isomorphism, it can be lifted along P. So what this means precisely is that we can find some morphism psi from E to E prime to some object E prime whose image under P equals phi. And the intersections of cofibrations and fibrations with weak equivalences also have a very simple intuitive explanation. The acyclic cofibrations will be just equivalences of categories that are injective on objects. That's basically known as an inclusion of a full subcategory. And acyclic fibrations will be fully faithful functors that are surjective on objects. So not just essentially surjective like for equivalences, but actually surjective. Yeah, so in this very simple example, all 5 classes of maps have a very explicit description. In fact, you can also easily see the lifting properties very explicitly. For example, let's do the lifting property of an acyclic cofibration along a fibration. So let's say a functor from A to B is an acyclic cofibration, which basically means it's an inclusion of a full subcategory. And a functor from X to Y is a fibration, meaning it's an isofibration. It has this lifting property for isomorphisms. Then the lifting property requires us to find a diagonal arrow. So you have a full subcategory of B, you have a functor from A to X, and you also have an extension of, if you compose this functor with a functor from X to Y, you have an extension to B. And you want to lift this extension to X. But this is a fairly tautological thing to do because so this functor on the left is a inclusion of full subcategories. Well, maybe I should have said more precisely full subcategories. Let's see, the inclusions of full subcategories that are equivalences. Otherwise, it can be confusing. So you have this inclusion of a full subcategory from A to B and it's an equivalence. So every object in B is isomorphic to an object in A. And this sort of already gives you a hint how to construct such lifts. So what's going to happen, you already know the value of this diagonal map on the image of A, and to extend it to the other objects in B, for every such object in B, you are going to choose an object of A isomorphic to it, and you are going to declare that the value of this diagonal map equals the image of this horizontal map on this object. This tells you what to do with objects, and for morphisms, you will use the lifting property for isofibrations to complete the construction of the lift. All right, any questions about this model structure? By the way, maybe I should mention that once you fix the category of small categories, and you say that equivalences must be precisely the weak equivalences, the rest of the model structure is determined uniquely. And that's why it's called the canonical model structure. There's exactly one model structure on the relative category of small categories, functors, and equivalences of categories. So that's what canonical means. It means there's only one in this context. All right, any more questions? Let me finish for today with a brief mention how model structures can be constructed in practice. I'm not going to comment on how to construct or prove the existence of a model structure in simplicial sets, which is something you must prove. Of course, I only constructed the classes of maps for you, but I didn't prove any properties for you. And of course, this is not entirely trivial. But assuming we already constructed a model structure on simplicial sets, it turns out it is quite easy to construct many more model structures. And here is there are basically two constructions that take care maybe of like 90% of what happens in model categories. And the first one is called a transferred model structure. And the way it works is you start with a model category C and a right adjoint functor R from D to C. Let me emphasize at this point is typically R is not a relative functor. Is not, sorry, we do not start with a relative category structure on D because we are now going to create weak equivalences on D using the functor R. And more precisely, if F is a morphism in D, we say that F is a weak equivalence or a fibration, or therefore also an acyclic fibration, if and only if its image under R is a weak equivalence fibration or an acyclic fibration in C. So the classes of weak equivalences, fibrations, and acyclic fibrations are transferred from C. And that's how the model structure on D is defined. There are two remarks to make here. One of them is that the transferred model structure does not always exist. So its existence is a separate property you must verify, which is in principle, in many cases, is easy to verify, and it's certainly easier than just verifying the axioms from scratch. And the other thing to mention, of course, is that I didn't say what happens to cofibrations, right? You may ask, well, what is happening to cofibrations? And of course, the point here is that in a weak factorization system, these two formulas tell you how to compute L if you know R, or R if you know L, right? So if you know L, then R is just precisely the set of morphisms, a class of morphisms with a right lifting property with respect to L. So in any model category, if you know the class of fibrations, and if you know the class of weak equivalences, and therefore you know also the class of acyclic fibrations, then you can recover the class of cofibrations as a class of maps that have a left lifting property with respect to all acyclic fibrations. So in any model category, if you know fibrations and weak equivalences, you also know cofibrations. Likewise, if you know cofibrations and weak equivalences, you also know fibrations. So knowing weak equivalences and one more class of maps determines the entire model structure. Okay, so let me give you some examples of transfer model structures. The first one was also already constructed by Quillen, and in fact, it was constructed in this manner. You have the category of topological spaces and continuous maps. And you have a singular simplicial set functor from topological spaces to simplicial sets. Turns out the transfer model structure exists. And in this context, it's known as a Serre model structure. If you may have heard in algebraic topology, people would sometimes talk about Serre fibrations. Well, a Serre fibration is precisely a fibration in this model structure. Is precisely a continuous map whose image under a singular simplicial set functor is a confibration. And cofibrations in the Serre model structure are very closely related to CW complexes. In fact, any CW complex is a cofibrant object in this model structure, and in the opposite direction, any cofibrant object is a retract of something that is called a generalized CW complex, where you relax one of the conditions in the definition. Yeah, so that's probably the quickest way to construct this model structure. So you just transfer it from simplicial sets. And just for fun, let me mention that in a completely similar manner, we previously talked about simply smooth sets, right? Sheaves of sets on the Cartesian side. And in a completely similar manner, you can transfer the model structure and simplicial sets using a smooth analog of the smooth singular simplicial set functor. Again, the model structure exists and has all sorts of nice properties. This was basically known to Szyszynski, I guess I should say here. Here are a few more examples. Simplicial objects with values in some algebraic structure, like abelian groups, which gives you what is called a simplicial abelian groups. Or in fact, it's not really specific to abelian groups. You can check pretty much any algebraic structure. You can Think of like simplicial monoids, simplicial groups, simplicial modules, simplicial rings, simplicial algebras, whatever. And all of those categories of simplicial objects, they have a forgetful functor to simplicial set, where this forgetful functor forgets the algebraic structure and preserves the simplicial set structure. And the transferred model structure always exists. This was also constructed by Quillen. And the third model structure, I guess, was also first constructed by Quillen. So maybe we should call it third Quillen model structure.
Could we think of this transfer model structure as like a left adjoint to forgetting the model structure on C in some sense? So having like a left adjoint to going from model categories to categories by just forgetting the structure?
Oh, there's a forgetful functor from model categories to the true category of categories, yes. And what is the question?
The question is if we could think of like taking this transfer model structure as the left adjoint to this functor.
Oh, let's see.
So in that sense, LD would be the model structure on D, and L is this left adjoint.
Let's see. It's not entirely clear to me, like if C is an input getter to the functor, right? How is D supposed to come into the picture?
So what I imagined was like this. So if you write down the adjunction, then you have this equivalence of morphism spaces. And then I think D and C are what this equivalence is natural in. And if you fix D and C, then you get like this universal property for these specific D and Cs, and then you should get out.
Oh, I see. Yeah, I see what you mean. Yes, it is true that you do have, yeah, I mean, the transferred model structure is the, let's see, I guess it's the terminal object in the slice category. Yeah. If you take the slice category of model structures over C, where a slice means an object will be a left Quillen functor. Sorry, I guess I should say a right Quillen functor to C. Then in this slice category, the transferred model structure, I guess, will be the initial object here. Because, well, I haven't talked about Quillen functors yet, but a right Quillen functor must preserve fibrations and acyclic fibrations. So from this definition, you can see that these classes of maps that you generate are the smallest possible classes of fibrations and acyclic fibrations. You cannot have fewer fibrations than the one we constructed. So it's quite literally the smallest possible class of fibrations and the smallest possible class of acyclic fibrations, which means that in the category of all right Quillen functors, or in the slice category of this model categories over C, well, I should really be a bit more precise. I guess this is what is called a, yeah, I mean, you take the slice category and then you take a subcategory on those objects whose underlying functor is R. And I'm not even sure how to denote this, but let me put a subscript R. So you take the slice category and then you extract those objects whose underlying functor is R. And then inside of this, you will see an initial object, which is the transfer model structure. Yeah. So it's but all what this is saying is that the transfer model structure is the model structure with the smallest class of vibrations and acyclic vibrations possible. So it's going to be an initial object among all such model structures where morphisms are right clone functors. Yeah. And I guess that's a good point to stop because I see it's already 10:43 here, so it's almost 2 hours. So if you guys have any questions, so let me know. All right, then I guess that's it for today. And next time we are going to look at how to apply this knowledge to construct model structures on various categorical entities we will need, like gamma spaces and Siegel categories and so on. So next time we'll put all of this into practice. All right, then thanks for listening, and I'll see you in 1 week. Do we want to keep the same time slot, by the way? Is starting at the same time a desirable feature for this semester, or?
Yes, for me, yes.
Okay, any other opinions?
It's fine for me.
All right, then I guess I'll see you at the same time next week. And have a nice rest of the weekend, I guess.
You too. Thank you. Bye-bye.
Bye.